dot, that means it's something out of the board, right? It's a vector out of the board. It's like that, I have a dot. If it's into the board, for example, if it's into the board, then I have put crosses. Right? That means it's into the board. This is out of the board, right? And there's a current J, then density J, and the B field outside here, it's Z direction, and it's Y and Z. So the current density is out of the board in the X direction, and the B field is in Z direction, and it's given by Q naught to okay. And it's on the other side, it's the other way around. Okay, this is from the inverse law. Now, if I have two of them, just like in plates of capacitor, two currents. Right? And one of them, the current is going outward, J, right? And in the other one, the current is going inward, also J, right? Okay, then you can just use principle of superposition. And the B field will be 0 outside, right? Just superimpose these two vectorially. P 0 here, P 0 here, and inside, I think my vector is correct. B field that way. B field is constant everywhere between the plates, and it's given by C direction is U naught J, right? Just the sum of U naught J over 2, and they add together inside the plates. Okay? Right. And I can also define surface charge density. Okay. For the mobile charge. Okay. And well, sigma. Okay, then J is just sigma times V. Okay. And V is the velocity of the mobile charge. This is just an analog to current density in GP, right? Current density in GP is rho times V. Okay. So, so with that in mind, we want to use this inverse steady transform. Recall that from chapter 5, if I have parallel plates moving, right? If I have sigma plus sigma minus sigma equals some velocity v, right? Then if the home frame of this capacitor, the parallel plate capacitor, the electric field is given by sigma over epsilon naught, right? But in the lab frame, and the electric field here, we're back in the discussion where the prime frame is the lab frame, right? So the prime in parallel is equal to parallel in perpendicular to the velocity, the direction of the velocity, is equal by gamma. So remember that, right? Okay. So we want to do the same thing now that includes B field, right? And now we have the tools because we have that parallel plates of current. So let's, this is where the drawing always gets confusing. So let's consider moving charge. So let me draw it, same thing here. So instead of a neutral plates with current, right? So we have a perfect balance between the mobile charge and the immobile charge. I'm just considering just mobile charge. In this case, there is no immobile. There is no immobile charge that make the plate neutral. So the plate is not neutral, right? That's why it's called charge shape. Think of having a conductor, say, well, not, or a plate, right? And I just charge it with plus anyway. And then I just physically, mechanically drag the whole thing with some velocity, right, in the x direction, right? And I have another one, so it's form of parallel plate. It's all minuses, right? And I also drag it this way with the same velocity, right? And this is, again, this x, y, z.
How is this different than having like a positive surface charge density? Because I thought like one's,
well,
is it? In this one, it looks like one's positive and one's
It's almost no difference, right?
Okay.
Well, I just want to make a distinction between these two discussions, right?
Mm-hmm.
Over here, I just have current, right?
Mm-hmm.
So it can be a neutral plate, except that you have current, right? So you have a perfect balance between the mobile plus charges, or whatever ion you have that's part of the crystal,
Mm-hmm.
or the metal, and then you have current flowing, right? So all you have is just current, but no residual charge. Here, I'm just considering charge on a plate that move.
Okay.
Right? So it's slightly different. Yes.
But a charged plate that's moving, isn't that just that? What's the
Yeah.
difference between that and
Because here there is electric field.
here?
Right? So, I mean, maybe it's all technicality of language, but at the end of the day, I want to consider electric field here.
Yeah.
And over there is no electric field, right? Here, there's two current sheet, there's only E field. No E field. E field is right? Because it's just current. And here is actually charge, right? So let me redraw it again like that, right? So this is the positive sheet, this is the negative sheet, and it's moving out of the port on this one, and then into the port on the other one. It's also out of the port, right? But because this is negative, the J is actually into the port. Right? The velocity is still out. The velocity, I'm pulling this to plate, pull it out in that direction, right? Okay? But the current is always defined as a positive current. So the effective current is actually going inward. Okay? So in this case here, as before, and the B field, I just look at magnitude, just look at the direction, look at the vector here. B field is given by U naught sigma times V, right? So the velocity is V, actually V naught. We confirm with the standard per cell. Right? And the magnitude of the electric field, there's electric field in this case, right? Because this is a positive plate, this is negative plate. There's an electric field going that way. Right? And the electric field is given by sigma. Okay? So now, let's orient we're going to boost that. We're going to move that around and look at it in different frames, right? I'm going to orient the plate this way. The plus plate, this is the minus plate, right? And I'm pulling it down with some velocity, that velocity. Okay? So to give you a B field, in this case, I'm just rotating that thing 90 degrees downward, right? So I have a B field that again goes that way. Okay? And the E field actually goes that way, right? Okay. So and this is again, this is called the O-frame, right? So this is E-mark, right? And then there's a Jarvis frame, right? But in this case it's all blank now, right? X prime, y minus y prime, minus z prime, okay? and then you swing it that way, right? So we want to see what is the electric field and magnetic field according to Charlie. Okay? Does anybody read Calvin Hobbes here?
Yes.
You all love Calvin Hobbes, right?
Yes.
You see how like here C and Hobbes has this couple of boxes. When it's facing up, it's a time machine, right? And facing sideways, it's a duplicator, right? When it's downward, it's a transformer power, right? So this is going to remind you a little bit of Kant. So it's facing this way. I mean, it's amazing what we can do with parallel plates, you know. I don't know. Anyway, let's move on. Right? Don't want to tell stories.
So how does turning them upside down change them from this one? It doesn't, right?
No, it doesn't. So
It's
just
the same.
remember
Okay.
the orientation, right? I mean, I'm going to move this around,
Yeah.
right? Because there's a rigidity here, right? If plus is on the left plate, and then there is the minus on the opposite plate, and it's moving in this direction, right? And then there is a B field. As a result, there's a B field like that, and a B field like that, right? Now I'm going to turn them around,
Okay.
right? And then move them around, right? So I'm going to turn them in such a way that the sheet is moving downward, right? And then, in this case here, it doesn't really matter in this case, but in this, let's say, Charlie is moving in over it with some velocity like that, so the plate is moving that way, right? Okay. Or you can see the Charlie moving to the left and the plate moving to the right. Okay. So then what happened? Then what Charlie saw is that because of length and traction, right? Because of Lorentz traction, the sigma that he sees is going to be equal to gamma sigma. Because of the contraction, the density is higher. Okay? But also, the velocity of the particle, the velocity of this sheet going downward, right? This is a different V naught prime is going to be 1 over gamma times V naught. You can either remember this from the velocity addition formula, so you recall there's 1 over gamma in there, right? But you can also think of it as a time dilation, because according to Charlie, image clock is slower, right? And as a result, the current that the velocity that is measured is actually less, right? Because the clock is slower. So in that case, then, so Charlie sees, of course, is a V prime, right? And V prime is in the x direction. And that's going to be equal to mu naught, because physics is the same, right? So mu naught has to be the same. Physics is the same in all dimensions, right? That's like Einstein. Mu naught is the same, right? And then you have sigma times V naught. Sigma prime, V naught prime, right? But this is just equal to mu naught gamma sigma plus 1 over gamma, which is just equal to the gamma cancel, 1 over gamma V naught, sorry. Okay? And this becomes just Vx. Right? So Dx bar, Dx prime is equal to Dx. Okay, and let's see, it's irrelevant here because we already know the result, but just for completeness, in this case, you also have an electric field in the y direction, dy prime. It's equal to dy. Or is that not dy prime? Is it equal to ui? No. No, right? There's an ey prime that's equal to gamma ui. Right? Because ey is the perpendicular reflection of the motion. Right? It's a perpendicular electric field. It's a transverse electric field. Okay, so we have transformation for the B field along the direction of motion. Let's orient the let's orient the B field differently. Orient them very differently. The next is let's orient the plane in such a way that it looks like this. The plus plate, there's a minus plate. Now it's moving in this direction in V naught. V in that direction and V naught, right? This is the O frame, and then Charlie's frame, O prime, this is X prime. I know in the past we always move things so that the plate is always moving to the right? But in this case here, for the case of simplicity that you will see later on, it's the O prime that's moving that way, the velocity. Okay, so effectively according to Charlie, this plate moves to the left. Again, there is an E field going that way. The E field in this case goes upward. In the direction. It's the Garfield and Hobbes thing. Okay. So in the rest frame, again, we already know the formula. EZ is mu naught sigma V naught, and then E, in this case, E is in the y direction, right? Y is sigma over epsilon. Okay. So it's boosted. So Charlie sees a different velocity. What is that velocity? According to special relativity, right? You don't have Galilean transformation. The velocity is a V naught prime is just V naught minus V over 1 minus V naught V over C squared. Right? Okay? Or if you want to express it in terms of beta, then beta naught prime equal to beta naught minus beta over 1 minus beta naught. Okay? That's the velocity of this plate that Charlie sees. Okay? This is going to be very similar to the discussion of two protons moving past one another or together, or the discussion on the forces due to a line charge or a wire. Okay?
Wait,
so
is this velocity the same as the one you see over here?
Yes, it's the same, right?
Because it's just, he's just looking at the velocity.
Correct, but over here, it's less critical. The discussion of the current is less critical, right? No, it's not less critical. This is the correct analysis. But here I have to know what is the velocity of the current moving in that direction.
Oh, okay.
Right. Here it's very simple because the the velocity V naught is perpendicular to the direction of the motion. Then
wait,
then
velocity.
This is the velocity addition formula is just that.
The velocity is perpendicular to the direction of
the velocity of V naught is perpendicular to the direction of x of the velocity of the frame. Right?
the frame is moving.
The frame is moving with velocity v in this direction or that direction, I don't care. Right? And then the plate is moving downward. Right? The plate moves downward, create a P field.
Oh.
Right? The plate, or you can just think of the charge, or the surface charge is moving down with velocity v naught. Right? And the velocity addition formula will give you this result.